Acid-base reactions are also known as neutralization reactions. So when you mix an acid and a base, you're going to get always a product that is going to be the same product in different types of neutralization reactions. And I will show you with a couple of examples later. Acid-base reactions are an example of double displacement or double replacement reactions. So you're going to have exchange of everything in your actual reaction, positive ions with negative ions, in a similar way to what you have with precipitation reactions. So right here, you have that for your neutralization reactions, you're going to get a salt or an ionic compound that is soluble in water, and also water as a product. So that product that I was telling you that it's constant in your different neutralization reactions is the water molecule. There are different definitions for acids, and I'm going over just one of them because it's the one that works with the examples that we're going to be doing. So arsenous acids are defined as substances that are going to dissolve in water to give you a proton or the ion of hydrogen. Acids and bases can be classified as strong or weak, similar to your ionic compounds. So whenever you have a strong acid, your strong acid is going to be classified as a strong electrolyte, and it dissociates entirely in water. So when you put a strong acid in water, you're going to get only the ions. There are no molecules left. Your molecule will be dissolved to give you only ions in solution. So acids are an example of a compound that is not ionic and it still gives you ions in solution. I have a list here with acids, strong acids, weak acids. I have two examples for weak acids. So your strong acids listed here, and actually every arsenous acid that we're going to be seeing in this lecture are covalent compounds. You don't have metals, you are sharing electrons, and still your acid will dissociate in water to give you the proton for hydrogen and the negative anion. So strong acids, I have a list of 6 acids that you should know. Nitric acid, sulfuric acid, perchloric, hydrobromic acid, hydroiodic acid, and hydrochloric acid. For weak acids, which are weak electrolytes and you have partial dissociation, I have just 2 examples here, and that's acetic acid, and this is hydrofluoric acid. So in a similar way to what we have for strong electrolytes, for your soluble ionic compounds and insoluble ionic compounds, we represent the dissolution of an acid in water. If it's a strong, 1 arrow pointing towards your product side where you have the ions. And then if it's a weak acid, we have a double arrow because your weak acid dissociates partially. You're getting the ions here, your positive ion and the negative one, but your ions can combine to give you back the molecule. So when you have a weak acid, you're going to have in solution your ions, but mostly your molecule right here, the molecule of the acid without dissociating. So for bases, we have the same thing. We have strong and weak bases. Now, the difference between the acid and the base, and this is still following Arrhenius' definition, the acid dissociates to give you the proton in water. A base dissociates to give you hydroxide in solution. So there you have your hydroxide. So still strong, still weak. And for strong bases, these one are easy for you to identify them. You're going to have a metal from group 1, an alkali metal, combined with the hydroxide ion. So I'm listing here some of them. And then I'm also listing some metals from group 2, calcium and barium. So those bases there are classified as strong bases, and then I'm giving you just one example for a weak base. It's a very interesting example because this weak base here, it does not act as an Arrhenius base. For you to have Arrhenius bases, that's your definition right there, you need to have your hydroxide as part of the formula. So all of these ones here are Arrhenius bases because you have sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide, and barium hydroxide. Now ammonium, right here, NH3, in the presence of water, the water is going to give a proton away. And then the NH3 molecule is going to bond with that proton, giving you NH4 and hydroxide. So I like to represent the water molecule like this. That is still H2O. Okay? But if you write down your water molecule like that, you can see that you have H plus OH minus. So this is just a bond between your H and the OH, okay? Because they're actually bonded together. So you have the positive ion, which is your H, and then you have the negative, which is the hydroxide. Okay? So if your water molecule acts as an acid, Arrhenius acids, it will dissociate to give you H plus in solution. Now your NH3 can take that H plus, and if you add NH3 plus 1 hydrogen, that will give you NH4. That is the ion of hydrogen. So you will have H plus, OH minus. So if you do NH3 plus, like addition, that will give you NH4 plus 1, which is that right there, your ammonium ion. And from the water, you're using the proton to form NH4, and what you have left is the hydroxide ion. So ammonia, even though it does not contain the hydroxide ion as part of the formula, when it dissociates in water, it's still forming hydroxide, because the hydroxide is coming from the ionization of your water molecule, giving you the proton that is going to form part of your NH3 molecule now to give you the NH4, and then you have your hydroxide ion right there. There are several things that we can use to identify substances as acids and bases. The most basic one is remembering the definitions. If you have acids, your acids are capable of forming H plus in solution. If you have a base, your base needs to be able to produce your hydroxide ion in solution. That's just one way. You should memorize the list of your strong acids. That will be very helpful. And you should know your strong bases too. Now we can also classify substances as acids or bases based on a numerical value. That numerical value is the pH. And the pH is just a measure of how much H plus you have in solution. H plus is what you're getting, the ion of hydrogen is what you're getting in solution from an acid. So the more H plus you have in solution, the more acidic a substance is. So there's a numerical scale that we use, and this is something that it's used in any general chemistry class from 0 to 14, but you can have negative values for pH There's a way of calculating pH values using an equation, and depending on your concentration, you can actually get a negative value for pH. The negative only means that your concentration of H plus is super high in solution. That's it. Now, using my pH scale here from 0 to 14, midpoint is 7. Anything that has a pH value between 0 and 7 will be classified as an acid. Anything that has a pH value between 7 and 14 is going to be classified as a base. Acids, H plus, bases, OH minus. So when you have something acidic, the concentration of H plus in solution should be higher than the concentration for hydroxide, or it will be higher. And then if you have a base, the concentration of your hydroxide now is going to be higher than the concentration of your H plus. At pH equal to 7, concentration of your acid is equal to the concentration of the base, and you have a neutral substance. It's not acidic or basic. So I have here several examples for neutralization reactions. I wrote all of the acids on the left and then followed by the base here. So I have all of my acids and all of the bases here. Different acids, different bases. So this is a double displacement reaction. So we're combining positive with negative. So my positive on the acid, it's going to be the H. H plus, Cl minus, Na plus 1, OH minus 1. So my positive combined with the negative of the base. H and OH, that is 2 H's, 1 oxygen, that's H2O, which is the water that I'm writing right here. And then the other two are going to combine to give you your ionic compound, which is the other product of your reaction. So the metal, Na, and the non-metal, Cl. Now when you write in your products, remember that you're combining the ions, no subscripts, nothing, just the symbol of your elements that you're combining. The positive one always goes on the left of your formula, positive and positive, positive and positive. So you're combining the symbol of your ions, no subscripts or anything. After you have them combined, you're going to check if you need a subscript based on the charges. Na is +1, Cl is -1. You don't need any subscript because your charges are going to cancel out. H is +1, so you need 2 H's to cancel out your -2 for oxygen. In the second example here, I have my positive, it's the H. The negative here on your base is the hydroxide. So H and OH, that will give you H2O. Then the other two are lithium and your nitrate. Lithium and nitrate. Lithium is +1, nitrate is -1, so you don't need any subscripts in that formula. Next example, same thing, H and OH, that gives you the water, and then the cesium ion and the bromide ion, they combine to give you your ionic compound, cesium bromide. And you can see that in this first three, actually in the 4 of them, but I want to go over this one after I finish with this. In these 3 here, we're getting water, and in the last one also water as a product. So water, it's the product of your neutralization reaction. So we're getting water, which is a neutral substance, as a product of a neutralization reaction. So that's why they're actually called neutralization reaction because the H from the acid is combined with the hydroxide of the base, giving you your neutral compound water. It's not that your solution is going to be neutral. Okay? That will happen with a specific type of acid-base reaction. Okay? Whenever you have a strong acid and a strong base, you're going to get a neutral solution. So all of these examples here are between strong acids and strong bases. You can check your list. You have all of these acids here listed as strong. You have these bases here listed as strong bases. So you are going to get a neutral solution. Now I have here another neutralization reaction. That one is between sulfuric acid and potassium hydroxide. Sulfuric acid, if you check your list of strong acids, going back, for all of them you have one proton, and one. The only acid that you have listed here with 2 protons is sulfuric acid. When you have 2 protons in your acid molecule, that's a diprotic acid. It means that your acid, strong acid, will dissociate in solution to give you two protons. So going back to my reaction here. To get the products of the reaction, you're combining the positive with the negatives. So my positive is still H. You have 2 protons because sulfate is -2 and each hydrogen ion has a charge of +1. So if you're combining hydrogen, the ion of hydrogen +1 with sulfate, your polyatomic ion sulfate with a charge of -2, to balance your charges or to have a neutral compound, same number of positive and negatives, you need 2 protons, 2 H plus to cancel out your -2 charge from the sulfate ion. So your acid is giving you a proton and your proton is combining with the hydroxide. But now, if you see, I'm writing down here my acid. I have 2 protons and that's H2, H and H, H2, and my sulfate ion. For my potassium hydroxide, I have K and hydroxide. So if 1 proton is combining with your hydroxide here, that will give you 1 water molecule. But you do have 2 protons. So what's happening in this reaction is that in this reaction, this is not a 1-to-1 reaction. It's not 1 mole of acid reacting with 1 mole of the base, which is what you have for all of these ones. You can check all of these 3 reactions and they are already balanced. You don't need to add any coefficients because everything will be 1-to-1. Now, in this case, when you have your diprotic acid, to neutralize 2 ions of hydrogen, you need 2 hydroxides. 1 hydroxide is not enough. 1 hydroxide is enough to neutralize 1 H plus with OH minus to give you 1 water molecule. But your acid is giving you 2 protons in solution. So you need 2 hydroxides to neutralize your 2 protons. So I'm writing my products here, just combining my positive with the negative, H and OH, that's H2O. And then I have K and sulfate. You don't have a subscript on K on this side because K is +1 and hydroxide is -1. So you don't need any subscripts. H2, I already told you. 2 H's because sulfate is -2. So when you're getting your products here, your K with your sulfate, K is +1 and sulfate is -2. So you need 2 K's to cancel out your 2 negative charges. That's why you need that subscript 2 right there. And then you have your water molecule. But this equation here is not balanced. You have 2 Ks and you have only 1 here. Okay. And then you have 2 hydrogens and you have, that's 2, 2. But you have another hydrogen here with your hydroxide. So the reaction is not balanced because you don't have the same number of each atom on both sides of your arrow. So you have to actually balance your reaction. So you can start by balancing your K, and that will give you a 2 in front of this one. And when you do that, now you have 2 H's and 2 H's, that's a total of 4, and you have only 2 on that side, so that will give you, now you need to add another coefficient in front of the water molecule to balance your hydrogens. Now you can check everything should be balanced. So what I did here, just balancing the reaction, is what I'm trying to show you right here. To neutralize your 2 protons, you need 2 potassium hydroxides. 2 hydroxides, 2 protons, and that will give you 2 water molecules. And then you have your 2 Ks that are going to combine with your sulfate to give you your K2SO4. So you need to know how to write down the products of your neutralization reaction, which is the same thing that we did with precipitation reactions. It's a double displacement reaction, so you're exchanging the ions. The ions of your reactant 1, you exchange those with the ions on your reactant 2. The good thing about neutralization reactions is that one of your 2 products is always water. So whenever you have a neutralization reaction, you can go ahead and write down water as one of your products, and then you can find out the other 2 ions. You can combine them to get that second product. Now we still have like some problems with stoichiometry. We have stoichiometry problems with precipitation, and we also have problems that we need to use stoichiometry with acid-base reactions. So a titration is something that we use to determine the concentration of an unknown solution. So you're using a solution that you know the concentration to find out the concentration of an unknown. So the setup for a titration is very standard. We have a burette, and in our burette we're going to have the solution with a known concentration, and that solution is known as the titrant. And then we have an Erlenmeyer flask right here where we're going to have the unknown. Okay? So a specific volume of a solution that we don't know the concentration. So we do a titration to determine how much volume we need from the titrant to reach an equivalence point in our titration. When you reach the equivalence point, you can use the moles of your known concentration and stoichiometry to find the moles of your unknown. That's what we do. So there are other things that are important in your titration. First, you need to be able to determine that equivalence point, and the equivalence point, we actually do not determine an equivalence point. We determine an end point for the titration, which is what we can actually observe by looking at a change in color. When you do a titration for, let's say, a strong acid and a strong base, we use phenolphthalein as the indicator, and an indicator is something that changes color depending on a pH. So phenolphthalein, it's clear when you have an acidic solution, which means that you have a solution with a pH that is lower than 7. And it's also clear when you have a neutral solution. So phenolphthalein in a solution that has a pH of 7 or any pH value lower than 7 will be clear. Your solution will remain as a clear solution. When you have enough phthalate in a solution that has a pH higher than 7, then the color is going to be pink. Okay? So if you have, for example, an acid in your flask, your initial color will be clear because you have something acidic. If you're using a base here as your titrant, when you're adding the base into your acid, your concentration of H plus is going to decrease because you're neutralizing the acid. The H plus from your acid is reacting with the hydroxide from the base, giving you water molecules. So if you start with an acidic pH and you're adding a base, your pH is going to start increasing, moving towards your 410, the highest number that you have in your pH scale. Okay? So the equivalence point and the end point should be similar. When you're doing a titration for an acid base, you're aiming to get a change in color that goes from clear to a very pale pink color. The lighter your pink color, the closer your end point is to the actual equivalence point of the titration. If your pink color is too dark, it means that you have too much of the base in your titration, which means that when you're doing your calculations, the volume of your base is going to be higher than the actual volume that you needed to neutralize all of your acid. So the number of moles of base that you're going to be calculating, it's going to be higher, and then you're going to get a number of moles of the acid that is higher, and the concentration for the acid that you're going to be calculating is going to be higher than the actual concentration. So the lighter the color, the better your titration, the better your final results. So I'm going to do an actual problem for the titration part. You should be able to know what a titrant is, and that's the solution with a known concentration. What's the analyte? A simple setup. You have a burette with your titrant, and you have your flask with the analyte. You need to know the definitions for endpoint and equivalence point. So I have here a problem, and this is a typical problem for a titration. I have actually two examples, and I want to do this one first. So in this example here, without even reading the problem, I'm going to go through the problem finding numbers. Okay? So I start with a volume of 38 milliliters followed by a concentration of 0.25, and that volume and that concentration corresponds to sodium hydroxide. Okay? It's right there, 38.25 sodium hydroxide. So I'm going to underline that with one color, because those two belong to the same substance. Your concentration of 0.25, molar concentration of sodium hydroxide, that means that you have 0.25 moles of sodium hydroxide in 1 liter for that solution. Okay? And so I keep going through the problem, and I have a second volume. That second volume corresponds to an acid. It's phosphoric acid, H3PO4. And if you remember about your sulfuric acid, for that one you had 2 protons, and in this one you have H3, so that's 3 protons. So I have a volume right here for my phosphoric acid. And what I want to calculate is molarity of the acid. So let's see what we can do. What can we find with the numbers that we have? What I need to find my final answer. So I'm going to write down first what I need to find my final answer. You're trying to find out a molarity. The molarity that you need to calculate is molarity for the acid. So I'm going to put molarity for H3PO4. Equation for molarity, moles over liters. If you want to calculate molarity for the acid, you need moles for the acid. It's not any number of moles. Molarity for the acid means that you need moles of the acid, and you need a volume of the acid too. So looking at your problem, to find the molarity, you already have half of what you need. You need moles and volume, and you have the volume for the acid right there. So you're given the volume, that number you have. What you don't have is the moles of the acid. You are given volume and concentration of sodium hydroxide. So for sodium hydroxide, you have 0.250 molar. That's moles. You are given a concentration and a volume for sodium hydroxide. So if you have volume and concentration, and look that I'm writing here my volume in liters, because molarity, it's moles per liter. That number, it's in moles per liter, so you need moles and liters right here. So if you have a concentration and a volume in liters, you can find out the moles of NaOH. So I'm going to calculate my moles of sodium hydroxide, because I have information that I can use to get that number of moles. So the moles of NaOH molarity times volume, that gives you your moles. So those are the moles that you have for sodium hydroxide. If you have a solution that is 0.250 molar of sodium hydroxide, in 38 milliliters of that solution with that concentration, you're going to have this many moles. So when you're doing the titration of your acid with an unknown concentration, this problem is telling you, okay, so you have 25 milliliters of this acid, you don't know the concentration, you know the concentration of sodium hydroxide, and from that solution you're using 38 milliliters to reach the end point of your titration. So when you get to the end point of your titration, you're using this many moles of sodium hydroxide. Since you have your equation right here, to neutralize 1 mole of the acid, you need 3 moles of sodium hydroxide. So we can actually find out how many moles of the acid you're neutralizing with these moles of sodium hydroxide that you have right there. So that's your next step. Because when you find out the moles of the acid, now you have everything that you need to solve your problem. And you're getting the moles of your acid using stoichiometry. From your reaction, you have 1 mole of the phosphoric acid neutralize with 3 moles of sodium hydroxide. 3, and this one is 1. Even though you don't have the number, that means that is 1. And that will give you 0.00317. So when you reach the end point of your titration, you're using that amount of moles of sodium hydroxide, which means that the number of moles that you have in your flask is equal to that number, 0.00317. So if you check your problem to find out the molarity of the acid, you need the moles of the acid and the volume. I already told you that you have the volume right there, and you just found the number of moles of the acid that you need. So you have one more step. Number of moles divided by your volume in liters, that will give you your concentration. And that's a concentration. It's close to 0.127. I'm just rounding, okay? So 0.127. So that's the concentration of the acid that you have. Your known, it's the base. You have a base with a concentration of 0.250. You're using that volume to reach the end point of your titration. With that information, you're getting the moles of sodium hydroxide. With the moles of sodium hydroxide, you're using stoichiometry to find the moles of the acid. And then finally, you can calculate the concentration of the acid, dividing your moles of the acid by the volume of the acid. So that's my second example, and it's a little bit different. So I'm going to tell you what you have to do, and then you're going to work the problem, and I'm going to tell you your final answer so you can compare your results. In this one, you have a volume and a concentration of the acid. So the first thing that you have to do is using those two to find the moles of the acid. Similar to what we did with the sodium hydroxide in the other problem. So you're going to find the moles of the acid, and let me see what you're trying to get. You're trying to get a volume of sodium hydroxide. So let me write down here . This is your unknown, volume of sodium hydroxide. So to find volume, you need molarity and moles. So you're going to use your volume and your concentration to find the moles of the acid. Then you're going to convert the moles of the acid to moles of the base using stoichiometry. Okay? So if you want the moles of the base, your factor, your conversion factor is going to be 2 moles of sodium hydroxide over 1 mole of the acid, sulfuric acid. Once you have the most of the base, now you are almost done. You're trying to find a volume, you have the most of sodium hydroxide right there from your calculation, and then you have the concentration of sodium hydroxide right here. So the molarity you already have. That number is the one that you need here. This one is the one that you need for your moles of sodium hydroxide. So you can just solve your equation to get the liters. And you're going to get something close to 0.05 liters, which you can convert to milliliters. So you should get something close to 50 milliliters.